The topic of the lecture for today is the SCF-MO of polyatomic molecules. The SCF-MO of the polyatomic molecules. We use the Schrödinger equation to solve polyatomic molecules using the SCF-MO method. SCF-MO stands for self-consistent field molecular orbital. The first subtopic is the approximation called the Oppenheimer Approximation. This approximation due to the kinetic energy of electron is much larger than the nucleus. Because of their size are really different. The second subtopic is the formulation of the Oppenheimer. The third, an application of the Schrödinger equation for solving the hydrogen atom, bring to the hydrogen molecular ion. We use the MO theory to solve this. The system contains only one electron. The fourth, linear combinations of the atomic orbital. This brings to the LCAO-MO method, or the linear combination of atomic orbital of molecular orbital. The fifth, use the Schrödinger equation to solve the hydrogen molecule ion and bring to solve the hydrogen molecule. Therefore, the hydrogen molecule contains 2 electrons. The sixth, diatomic molecule. There are 2 types of the diatomic molecule. One is the homonuclear diatomic molecule. This may contain many electrons. The seventh, the heteronuclear diatomic molecule of any molecules contains also many electrons. The eighth, the linear combination applied on the symmetry adaptation. The ninth, the MO model. This is a model of the molecular orbital. The last one is the calculation of electronic structure. Normally we call the optimization of the molecules. The Oppenheimer approximation was found by Max Born and J. Robert Oppenheimer in 1927. The Oppenheimer approximation is the assumption that the electronic motion and the nuclear motion in the molecules can be separated. It separates electron and nuclear motions based on the idea that nuclear mass is so much larger than electron mass. that the nuclei are basically fixed particles. It means that the kinetic energy of the electron is much larger than the kinetic energy of the nucleus. For the figure, compare the size of electron and nucleus. The Oppenheimer approximation is the first of the several approximations made when trying to solve Schrödinger equation for more complex systems than one or more than two electrons. For one electron is the hydrogen atom. The simplest molecule as the molecule ion is the hydrogen molecule ion, or is the molecule contains only one electron. For the two electron system is the hydrogen molecule, which is the simplest molecule. As the molecular potential energy curve of the atomic molecules shown in figure 2.1 is a representative of the polyatomic molecules, the Oppenheimer approximation was applied. A potential energy surface of the polyatomic species, and to identify the equilibrium conformation of the molecule with the lowest point on this curve. It was concluded that the Oppenheimer approximation is very reliable for Gauss electronic states, but it is less reliable for excited states. This is the minimum of the potential energy. R0 is the equilibrium internuclear distance. This figure shows the molecular potential of the hydrogen molecule as the representative of diatomic species. The simplest approach to the formulation of the Oppenheimer approximation is to consider a one-dimensional analog of the hydrogen molecule ion, in which all motion is confined on the z-axis, as shown in the figure 2.2. It's composed of two hydrogen atoms and one electron. Each charge of this hydrogen molecule is the ion. The full Hamiltonian operator H can be written as shown in equation 2.1. The first term we can chart as the symbol Te, which is the kinetic energy of electron. The second term is the kinetic energy of the nucleus, and The third is the potential energy. C means the position on the z-axis. Capital C1 and 2 are position of hydrogen 1 and hydrogen 2. Therefore, the Schrödinger equation can be written as a function of small z and capital C1, 2, as shown in the equation 2.3. Based on the Oppenheimer approximation, the wave function needs to be separated into the electronic wave function and the nuclear wave function. The sign symbol of the first term is the notation as size is a function of the small c, or the position of electron, and the position of the nuclei C1 and C2. For the nuclear wave function, we use the chi symbol as the wave function. If you replace the Hamiltonian operator equation 2.2 and wave function 2.4 into the Schrödinger equation 2.3, we will get the equation 2.5. Now we have the unknown term as the W letter. This term is defined as following equation. From the previous slide, the quantity W is non-zero because the wave function of electron depends on the nuclear coordinates. So, the term of the partial differentiation on the electronic wave function with respect to the position C of J particle is non-zero. However, because of the nuclear masses occur in the denominator, we suppose that the quantity W is so small and can be reduced. Instead of the equation 2.5, we try to solve the equation 2.7. If we rearrange the equation 2.7, we will get the equation 2.8. The first term, the most left term, when the nuclear coordinates are fixed. Therefore, we can neglect this term, and the equation will be short as the equation 2.9. The energy of system becomes the energy of electron, which depends on the coordinates of the nuclei. C1 and C2. On substituting equation 2.9 into equation 2.8, we obtain the equation 2.10. The equation 2.10 is the Schrödinger equation for the electron in a potential V that depends on the fixed locations of the two nuclei. The solution is the electronic wave function, and the eigenvalue E of electron depends on the position of nuclei C1 and C2. The eigenvalue is the electronic contribution to the total energy of the molecules plus the potential energy of internuclear repulsion that the p-selected nuclear locations. It is this function that, when plotted against the nuclear position, gives the molecular potential energy curve. From the equation 2.10, if we cancel the electronic wave function, then we get the equation 2.11. E subscript small e is the electronic energy in the field of the nuclear potential energy and has the form of the molecular potential energy curve. Its eigenvalue capital E is the total energy of the molecule within the bond Oppenheimer approximation. Due to the equation 2.9, the Schrödinger equation and Hamiltonian operator can be shown using the normal symbol for the potential energy and the total energy as shown in the equation 2.12 in the next slide. As mentioned in the previous slide, equation 2.12 is the normal Schrödinger equation. H operates on the electronic wave function equal to the eigenvalue energy E operates on the electronic wave function. The Hamiltonian H is equal to minus h bar square over 2 times m subscript small e multiplied with the Laplacian operator plus potential V. For the potential V is the potential energy of electron, but in the field of the stationary nuclei plus the nuclear interaction contribution. The right term of the equation 2.12 is the energy. E is the total electronic energy plus nucleus repulsion energy. For a stationary nuclear conformation. This slide shows you an application of the Oppenheimer approximation on the hydrogen molecule ion. Sometimes we call hydrogen molecular ion. They are the same. The formula of the hydrogen molecule ion is H2 plus. It means its charge is the positive charge. Even though within the Oppenheimer approximation there is only one molecular species for which the Schrödinger equation can be solved exactly, is the hydrogen molecule ion. Just only one ion can be solved exactly using the Schrödinger equation. You must remember that. For the Hamiltonian operator of the hydrogen molecule ion can be written as the equation 2.13. The first term is the kinetic of the electron. The second and the third term are the energy according to the interaction between electron and nucleus of the hydrogen Ha and Hb respectively. The last one is the repulsion energy between the two nucleus, or we call nucleus interaction energy. As the hydrogen molecule ion has only one electron, it has a status in valence theory analogous to the hydrogen atom in the theory of the atomic structures. Just as the Schrödinger equation for the hydrogen atom is separable and solvable when expressed in the spherical polar coordinates, so the equation for the hydrogen molecule ion can be also separable and solvable when expressed in ellipsoidal coordinates. This is denoted by mu, nu, and phi, where mu and nu are shown in the equation 2.14. As referred to the figure 2.2. Ra, Rb is the interdistance between electron and nucleus of the hydrogen A and hydrogen B respectively. For capital R is the nuclear interdistance between the two nucleus. Phi we call azimuthal angle. In these coordinates, the two nuclei lie at the foci of the ellipsoids of constant mu. The resulting solutions are called molecular orbitals and assemble atomic orbitals, but spread over both nuclei. The figure 2.3 shows the molecular potential energy curves of the hydrogen molecule ion, which vary with the internuclear distance, capital R. The two lowest curves are the greatest interest, and we concentrate on them. The steep rise in the energy as the internuclear distance are approached to zero is largely due to the increase in the nucleus potential energy. As the two nuclei are brought close together, consideration of the previous figure diagram or the potential energy diagram of the hydrogen molecule ion, figure 2.3. We can see that at large distance, at the R approach to the infinity, the curve tends towards the values typical of a hydrogen atom with the second proton a long way away. The hydrogen molecule ion, the lowest curve pass to a minimum close to or equal to 2 times of the A0 unit, this point. And its energy deadline about the 0.20 of the energy unit HCRH. The value of 2.2 RCHR is equivalent to the 2.7 electron volt. Below the energy of a separated the hydrogen atom and the proton H+. It means that if we separate the hydrogen atom of the hydrogen molecule ion, it can be the hydrogen atom and the proton are far away. The result suggests that the hydrogen molecule ion is a stable species in the sense of the having a lowest energy than its dissociation products, but not a chemical sense of the being non-reactive, and that its bore length will be close to the 2A0 unit. This distance is equivalent to the 106 picometers. The species is known spectroscopically. Its minimum lies at the 2.648 electron volt, and its bond length is 106 hygrometer. It means that the theory and the experiment are close. Using the previous diagram, figure 2.3, to describe the lowering of energy of the hydrogen molecule ion. The origin of the lowering of energy can be found by examining the form of the wave functions. The figure 2.4 shows the two molecular orbitals of the lowest energy as the two curves on the 1 sigma and 2 sigma potential. Figure 2.4 shows the bonding orbital. This is the 1s orbital as the stable as the lowest energy of the lowest curve. The second is the anti-bonding orbital. This is the 2s orbital according to the top 2 sigma curve. The method to calculate using the Schrödinger equation and using the wave function, including the method of the LCAO approximation. This method I will give you later. This slide shows you a topic of the molecular orbital theory or the MO theory. It is very difficult to get the solution using the Schrödinger equation, even though including with the Oppenheimer approximation. The exact solution for more complicated molecules are hardly ever obtained. Therefore, we must resort to another approximation, but use the exact solution for as a guide. Another reason why making a further approximation is quite sensible is that we already have available quite good atomic orbital for many electron atoms, and it seems appropriate to try to use them as a starting point for the description of many electron molecules being from those atoms. This means that the MO for many electron molecules, we should apply the further approximations. This slide shows you a linear combinations of atomic orbitals as a method. Inspection of the form of the wave functions for hydrogen molecule ion as shown in figure 2.4, the previous figure. The figure suggests that they can be simulated by forming linear combinations of hydrogen atomic orbitals. The first molecular orbital show you the left hand side. This molecular orbital can be combined as the constructive interference. This molecular orbital corresponds to the bonding orbital 1 sigma. The right hand side, the orbital corresponds to the anti-bonding orbital or 2 sigma orbital. The phi A, phi B are the 1s orbital on the nucleus A and nucleus B respectively. In the partial justification for simulating molecular orbitals as an LCAO, it stands for a linear combination of atomic orbitals, can be appreciated by examining the Hamiltonian for the problem given in equation 2.13. When the electron is close to the nucleus A, it means that the Ra is much more less than Rb. And the Hamiltonian is approximately to this term. The third term of the equation 2.13 can be removed and obtain the equation 2.16. Apart from the final constant term, this Hamiltonian is the same as that for a hydrogen atom. Therefore, close to nucleus A, the wave function of the electron will ensemble a hydrogen atomic orbital. The same is true close to B. And this form of the solution is captured by the two linear combinations as constructed above. This slide shows you two affine linear combinations of atomic orbitals. The same conclusions can be reached in a more formal way, one that is more readily extended to other species. By writing the molecular orbitals or MOs as the following LCAO, as shown in the equation 2.16. To build the molecular wave function left hand from the linear combination of atomic orbital phi r. This equation therefore called as the LCAO-MOs method. This means that we construct the molecular orbitals from the atomic orbital using the LCAO method. The atomic orbitals used in this expansion constitute the basis set for the calculation. In principle, we should use an infinite basis set for a precise recreation of the molecular orbital. But in practice, only a finite basis set is used. We shall assume that the members of the bases are real and that each one is normalized to unity. The optimum values of the coefficients are found by applying the variation principle method. This means that we have to solve the circular equations as shown below. The summation of coefficient C are multiplied with term H subscript Rs minus E times S subscript Rs equals 0, where the Rs is a metric element of the Hamiltonian, and the S subscript Rs is an overlap metric element. These circular equations have non-trivial solutions only if the circular determinant vanishes. We write this condition as the equation 2.19. Determinant H minus E S is equal to 0, where H is the matrix of elements H subscript Rs, and matrix S is corresponding matrix of elements S subscript Rs. To make progress with finding the roots of the determinants H minus Es, we need to evaluate the relevant matrix elements. For a basis of two atomic orbitals, one on atom A and the other on an identical atom B, the circular determinant 2 times 2 its elements can be written as following equations. SAA equal to SBB equal to 1. SAB equal to SBA equal to S, where S is the overlap integral. For the Hamiltonian matrix, its elements HAA equal to HBB and assigned to be the alpha value. For the HAB equal to HBA is assigned to be the beta value. Alpha and beta are the molecular Coulomb integral and the resonance integral, respectively. The circular determinant 2 times 2 can be therefore written as the equation 2.22. Showing the equation 2.22 and its roots are E plus equal to alpha plus beta over the 1 plus S, and E minus is equal to alpha minus beta over the 1 minus S. This slide just shows you the diagram to get more understanding to get the circular equation 2.22. If we solving the C coefficient using the equation 2.18, we can get the CA equal to CB, and CA can be equal to 1 over square root of 2 times 1 plus S. For the E plus energy is equal to alpha plus beta over 1 plus S, as shown in equation 2.24. CA is equal to minus CB. Therefore, CA is equal to 1 over square root of 2 times 1 minus S. For the energy, E minus is equal to alpha minus beta over 1 minus S. For the value of the alpha beta, we can compute using the equation 2.26 and 27 respectively.